with a setUID exploit. I had a setUID exploit for this setUID binary called libvirt proxy, which was on Xen-based Red Hat boxes, which would essentially launch and sit there, wait for you to send it some commands, and then had a stack-based overflow, which was perfect for this scenario, since we could launch the libvirt proxy, run our kernel leak, and try to leak out enough information from the task struct or other VMA information in the kernel to be able to bypass the ASLR. My exploit only worked on 32-bit simply because it just brute forced its way through the address space and ran it a bunch of times and eventually succeeded. But you could exploit this pretty easily on 64-bit by leaking information about where the stack base was located. And you can actually, similar to userspace, pair up an information leak with another exploit targeting the kernel. The stack canary value from the config cc stack protector protections is located in the task struct, which may be able to be leaked through some of these memory disclosures. Some of the memory disclosures are very small, such that you have maybe a statically allocated structure on the stack, and you fill in a couple values and then sort of copy to user back that entire struct. And due to paddings of the compiler, there might be a few holes in the struct of padding or uninitialized information which can be leaked back. But sometimes we have great ones that, for example, this SCTP, again, another vulnerability in the SCTP subsystem, in the git sock option, which was also where the OpenBSD one was in git sock op. These are very common areas, where we actually control the length value coming into this function here. And as you can see, the length value is, they make sure that it's not too small, but they don't make sure it's too big. So you pass in this length value with your git sock opt, and what it will do is copy back pretty much an arbitrary amount of memory, kernel memory, back to user space through this last copy to user here, taking in the length value. It's only meaning to copy this very small structure of the HMAC values, but in actuality, you can leak a whole lot of kernel memory. Race conditions, I'm getting pretty late on time. Maybe we'll skip through that. There's some great work trying to exploit these on uniprocessor machines, where you can actually force the kernel to sleep or reschedule processes in certain code paths. But of course, if you're on SMP, you can easily exploit these by having multiple threads in a race condition. This is a very simple example showing that a length value was copied from user space with this getUser function. It went through a sanity check, but then later in that function, they actually recopied the length value from user space without actually doing any validation. So even though it was copying the same memory address in both of these getUser calls, there's this window of time where we would actually be able to race and change the value that is trying to retrieve here in between these two getUser calls. So it could pass the validation in step 3. We can change it. It will copy in the new malicious value, and then it will do a copy from user with this malicious length value, allowing us to overflow. I think this was a k-mallet buffer. And last, there's these great bugs in the memory manager. The memory manager is a very complex system which is essentially in charge of bookkeeping all of the state, all of the various VMAs, all of the protection flags, and it does some complex splitting and merging of these various VMAs that can be desynchronized from what the actual state is in memory. And if you guys follow the PS3 hack, the George Hotz guy did this with the OS and hypervisor, where he was able to do a lot of allocations and deallocations and actually able to desynchronize the state of the memory manager from what was actually in physical memory based on actually glitching the memory bus while these memory mappings were happening. So he actually had physical access to the PS3 and was glitching the physical bus line on the PS3. Now we can do the same thing for the kernel but instead of actually glitching the bus on our machine, we're just sort of taking advantage of a bug that throws off the bookkeeping of the So there's some really awesome exploits from the guys at isec.pl. These were old, but they're still incredibly awesome. I think they're from 2003. mremap. There's a mremap unmap one, and there was a dbrk, which if you look at a very simple explanation of this, we have our user space, which is our virtual address space, which is shared both by the user space and the kernel space. And what we can do with the BRK function call is expand the area of memory that's usually used for the heap. And unfortunately, they didn't actually do proper sanity checking on how far you were expanding this heap. So we could actually expand the heap past where the kernel address space starts and overlap our heap with the kernel address space. And then when we call mprotect to modify the protection, since the kernel address space is protected with the page table permissions, mprotect would say, hey, this memory is part of the heap. I'll go ahead and modify those MMU values for you. So then kernel address space becomes writable by user space, and you can escalate your privilege that way. So we're about out of time. I'm going to wrap up quickly. For researchers, I really encourage everyone to spend a lot more time in kernel space. There's a ton of interesting bugs, interesting vulnerabilities, and interesting exploits. For administrators, a lot of these distributions are very conservative in nature. They will not apply these security features, even if they're available, simply because there can be performance impact, there can be compatibility issues. So if you are really concerned about this, prod your distros to start deploying some of these protection mechanisms. And there is a lot of hardening you can do on your own through these patch sets, which aren't included in mainline, such as JR security packs and the current heap ones that I've mentioned so far today. And you should definitely be sponsoring and supporting these guys who develop these patch sets, because they're the ones who actually have a big impact on Linux kernel security. So before I sign off, we released a tool which allows you to audit your kernel config, both from your running kernel or from a kernel config on disk. It's based off this checksec tool from Tobias at TrapKit, which is pretty good for auditing user space stuff. Auditing whether you have NX and RELRO and PIE and everything for your user space binaries. And I've added kernel support so we can check for a whole bunch of commonly forgotten config options which can help harden your kernel against attack, and you can download the patched version there. And the takeaway of this presentation is not to scream about how insecure Linux is. As we all know, security is not a binary state. It's not either secure or not secure. Most of security is trying to deal with this uncertainty and develop some sort of risk management around this uncertainty. I love this quote from Rumsfeld where he says, there are known knowns, there are known unknowns, and there's also unknown unknowns. It's a very jumbled quote, but it actually has some applicability to security, as he says in each year we discover a few more of these unknowns. So hopefully the unknowns that we discover this year won't be as severe as we saw in 2008 and 2009. But if you prefer a more simple quote, we have G.I. Joe here saying, now you know, and knowing is half the battle. And with that, I'll open up for any questions from you guys. Thanks a lot. No questions?
I have a comment.
All right.
So you showed a comparison of Linux kernel bugs versus Windows and OS X, and I know you weren't implying this necessarily, that it means the kernel's better. It's just that because of the lack of remote access and because of researchers such as yourself and others are concentrating more on these local, kernel exploit issues. It would not surprise me at all to see equivalent issues that are happening within Windows and in other environments that are rough analogs. It just might be that there's more attention, that there are more people paying attention to Linux kernel, perhaps because it's open source.
I agree. I don't know if we can get that on tape, but yes, I agree with that point.
I think I would argue that if that's the case, that more people are paying attention to Linux kernel, it's because generally compromises in the Windows world mean full system level compromises or admin level compromises. Whereas with Linux, you're generally running as a limited user most of the time. And in Mac OS X, well, nobody's paying attention because we've got a market share there, or a very large one.
And there's actually been a flurry of there was a lot of local denial of service in the last patch Tuesday, and I think there was a one or two local privilege escalations in the Windows kernel recently too. So it's not like they're not found there. I think attackers just concentrate on different goals. On a Linux box, you might want to maintain a better foothold in this environment that might be more monitored by administrators. When on a Windows box, the general Windows user might not be as aware, or you might not need as sophisticated rootkits to hide from that user. So it can be a difference in environments or attackers' incentives and goals.